Now let's have integration using algebraic substitutions. So why is this integration method called algebraic substitution? It's because the process of substitution involves only algebraic terms. And what is new with these algebraic substitutions? We will be dealing with irrational integrands. Integrands of the form, say, integral of dx over square root of x plus cube root of x. Also have integral, the product of 4x plus 3, and the square root of 1 plus 2x dx. And the integral of dx divided by the product of x squared and the quantity 1 plus x raised to 4 all raised to 3/4. The algebraic substitution to be made depends on the irrational integrand under consideration. In short, there is no general rule. Let us recall irrational functions. What are irrational functions, by the way? Irrational functions are algebraic functions involving one or more radical polynomials. Let's start with case number 1. When the integrand contains fractional powers of x only. If our integrand contains fractional powers of x only, then we use the substitution. We let z equals nth root of x, which implies that z raised to the power of n is equal to x, where this n is the least common denominator, or LCD, of the fractional exponents of x. Example, the integral dx over square root of x plus cube root of x. Since the square root of x is equal to x raised to 1/2, and cube root of x is equal to x raised to 1/3, then n, which is the least common denominator, the fractional exponents of these two terms, n is equal to 6. Hence, we let z equals 6th root of x, which implies further that x is equal to z to the power of 6. Differentiating x with respect to z, we get dx is equal to 6 times z to the power of 5 dz. Therefore, we can express square root of x as z raised to the power of 3. But how did we get z raised to the power of 3? Since the square root of x can be expressed as x raised to the power of 1/2, we multiply our n, which is 6 to 1/2. And so we get z raised to the power of 3. And cube root of x can be expressed as z raised to 1/3 times the value of n, which is 6. And so we get z raised to the power of 2, or z squared. Given this information, we substitute 6z raised to the power of 5dz to dx, and square root of x is replaced by z raised to 3, and cube root of x is replaced by z raised to 2. Applying integral of the product, we have 6 times the integral of z raised to 5 all over z squared times the quantity z plus 1 dz. We have 6 times the integral of z cubed all over z plus 1 dz. How did we get the expression inside the quantity? We performed polynomial long division to the previous integrand. We divided z cubed by z plus 1. And applying the rule of polynomial long division, we get z squared minus z plus 1 minus the remainder 1 over z plus 1. Then, we apply integral of sum or the linearity rule. Then, getting the integral or evaluating the integral of each integrand, we get 6 times the quantity z cubed over 3 minus z squared over 2 plus z minus the natural logarithm of z plus 1, or the natural logarithm of the absolute value of z plus 1 plus c. Distributing 6 to each term inside the quantity, we get 2 times z cubed minus 3 times z squared plus 6 times z minus 6 times the natural logarithm of the absolute value of z plus 1 plus c. But wait, what is the value for this z? Z is, by the way, take note, z cubed is equal to the square root of x. Z squared is equal to the cube root of x. And z is equal to the sixth root of x. Substituting these values to the z's, we get the final answer. The integral of dx all over the square root of x plus the cube root of x is equal to 2 times the square root of x minus 3 times the cube root of x plus 6 times the sixth root of x minus 6 times the natural logarithm of the absolute value on sixth root of x plus 1 plus c. Let's have case number 2. Case number 2 is applicable when the integrand contains fractional powers of a plus bx only. If our integrand contains fractional powers of a plus bx, then we use the substitution z is equal to the nth root of a plus bx, which implies that z raised to the power of n is equal to a plus bx, where n is the least common denominator, or LCD, of the fractional exponents of the expression a plus bx. Example, we are to evaluate the integral of the product of the quantity 4x plus 3 and the square root of 1 plus 2x dx. Take note, our integrand contains the expression a plus bx, the form of square root of 1 plus 2x. Therefore, we let z equals the square root of 1 plus 2x, which implies that z squared is equal to 1 plus 2x. Solving for x, we get x is equal to z squared minus 1 divided by 2. And differentiating x with respect to z, we get dx is equal to z times dz. Given that z is equal to the square root of 1 plus 2x, dx is equal to z squared minus 1 all over 2, and the derivative of x is equal to z dz, then we transformed our integrand into the form the integral of 4 times the quantity z squared minus 1 over 2 plus 3 times z dz. But wait, where did we get this quantity z squared minus 1 all over 2? Examining our original integrand, we know that we have 4x plus 3 times the square root of 1 plus 2x dx. Taking into account this 4x plus 3, we know that x is equal to z squared minus 1 all over 2. So we substitute this value of x. And we all know that square root of 1 plus 2x is z itself. And dx is z dz. So what we do here is we just substituted these values of z, x, and dx. Manipulating algebraic terms, we get the integral of the quantity 2z squared plus 1 times z squared dz. Using distributive property, we get the integral of the quantity 2z raised to 4 plus z squared dz. Then we apply integral of sum or linearity rule, then use the general power rule. So we get 2z raised to 5 all over 5 plus z raised to 3 over 3 plus c. Substituting the value of z, we get 2 times the quantity square root of 1 plus 2x raised to 5 all over 5 plus square root of 1 plus 2x raised to the power of 3 over 3 plus c. Simplifying further, we get the product of 1 plus 2x raised to the power of 3 halves and the quantity 12x plus 11 divided by 15 plus c. Let's have case number 3. Case number 3 is applicable if the integrand contains the expression x raised to the power of m times the quantity a plus b times x raised to n all raised to the power of p over q, where m, n, p, and q are integers, and n and q are positive integers. And if m plus 1 divided by n will result to one integer. These conditions are all satisfied. Then we use the substitution z is equal to q root of a plus b times x raised to the power of n, which implies further that z raised to the power of q is equal to a plus b times x raised to the power of n. Let's have this example. We are to evaluate the integral of x cubed times the square root of 1 plus 4x squared dx. First, we need to satisfy all the conditions. Let us satisfy that m plus 1 divided by n is an integer. We have m is equal to 3, n is equal to 2, so we have m plus 1 divided by n is equal to 2. And 2 is an integer. Now, since we satisfy the condition that n plus 1 divided by n is an integer, then we use the substitution z is equal to the square root of 1 plus 4x squared, which implies that z raised to the power of 2 is equal to 1 plus 4x squared. Given this equation, we solve for x in terms of z. So we get x is equal to the square root of z squared minus 1 divided by 2. Differentiating x with respect to z, we get dx is equal to z dz all over 2 times the square root of z squared minus 1. So, we transform our integrand. We all know that x is equal to the square root of z squared minus 1 all over 2. So we substitute this value of x to the original integrand. So we have the quantity of square root z squared minus 1 divided by 2 all raised to the power of 3. And we all know that square root of 1 plus 4x squared is equal to z. And so we substitute z. Dx is equal to z dz all over 2 times the square root of z squared minus 1. And so we substitute this expression to the given integrand. Manipulating algebraic expressions, applying laws of exponent, then applying integral of the product, we multiply 1/8 times 1/2 times the integral of z squared minus 1 times z squared dz. Simplifying further, we get 1/16 times the integral of z raised to the power of 4 minus z squared dz. Applying integral of sum or linearity rule and applying power rule, we get 1/16 times the quantity z raised to the power of 5 divided by 5 minus z cubed over 3 plus c. I'm substituting back the value of z, which is equal to the square root of 1 plus 4x squared. We get 1/16 times the quantity square root of 1 plus 4x squared raised to 5 all over 5 minus the quantity square root of 1 plus 4x squared raised to the power of 3 divided by 3 plus c. Simplifying further, we get the final answer. And so integral of x cubed times the square root of 1 plus 4x squared dx is equal to the quantity 1 plus 4x squared all raised to the power of 3/2 times 6x squared minus 1 all over 120 plus c. Let's have case number 4. This is applicable if the integrand contains the expression x raised to the power of n times a plus b times x raised to the power of n all raised to the power of p over q, where m, n, p, and q are integers, and n and q are positive integers. This is somehow similar to case number 3. But what makes it different is that our second condition states that m plus 1 divided by n plus p over q will result to an integer. If these conditions are met, then we use the substitution. The product of x to the power of n and z raised to the power of q is equal to a plus b times x to the power of n. Example. Evaluate the integral gx all over x squared times the quantity 1 plus x raised to 4 all raised to the power of 3/4. First, we are going to check if the conditions are met, so we can use case number 4 substitution. Let m equals -2. But why -2? Take note that in the given integrand, the expression is in the denominator. So that is why m is equal to -2. N is equal to 4. P is equal to -3, and Q is equal to 4. Let's check if this condition is satisfied. N plus 1 divided by n plus P over Q will result to an integer. Aha! It results to -1, which is an integer. And so the conditions are met. So we can use the substitution under case number 4. And the substitution states that the product of x raised to the power of n and z raised to the power of q is equal to a plus b times x raised to the power of n. Substituting the values of n, q, we get x raised to the power of 4 times z raised to the power of 4 is equal to 1 plus x to the power of 4. Solving for x, we get x is equal to z raised to the power of 4 minus 1 all raised to the power of -1/4. Differentiating x with respect to z, we get -z cubed times the quantity z4 minus 1 all raised to the power of -5/4 dz. Now we can substitute these values to the given integrand, so we can transform the integrand and do some algebraic manipulations. We substitute the value for dx. We substitute the value of x. And the value of 1 plus x raised to the power of 4 all raised to the power of 3/4. So what happened here? In the denominator, we simplify first that quantity x raised to the power of 4 raised to the power x raised to the power of 4, sorry, x raised to the power of 4 times z raised to the power of 4 all raised to the power of 3/4. Applying laws of exponent, x to the power of 4 raised to the power of 3/4 is simply x raised to the power of 3. And z raised to the power of 4 raised to the power of 3/4 is simply z raised to the power of 3 and copy the other terms of the integrand, of the transformed integrand. And what is new here? In the second step, or in the second part of the solution, we arrived with x raised to the power of 3 in the denominator. And we all know that x, as given in the previous information, is equal to the quantity z raised to the power of 4 minus 1 all raised to the power of negative 1/4. So we substitute this value to x. And so we have, in the denominator, we have this new substituted value of the quantity z raised to the power of 4 minus 1 all raised to negative 1/4 raised to the power of 3. One must be very careful in manipulating these algebraic expressions and in applying laws of exponent. In applying laws of exponent to the expressions in the denominator, we get these new expressions in the denominator. We have z raised to the power of 4 minus 1 all raised to negative 1/2. Because negative 1/4 raised to the power of 2 is equal to negative 1/2. And negative 1/4 raised to the power of 3 is equal to negative 3/4. And so we have these new expressions, derived expressions in the denominator. Then we copy the terms in the numerator. Then we simplify the operation in the denominator. Since our denominator contains expressions of the same basis, then we perform laws of exponent. And we all know that when we multiply two terms or terms with the same basis, we only add their exponent. And so we have this new derived expression in the denominator, the quantity z raised to the power of 4 minus 1, all raised to the power of negative 5/4, then copy z to the power of 3. What do you think will happen next by examining this new transformed or this transformed integrand? You get it right. We can eliminate the common expressions in the numerator and the denominator. We have the expression quantity z raised to the power of 4 minus 1 raised to the power of 5/4. This can be eliminated. And also, the expression z to the power of 3, which is common both in numerator and the denominator. So we can eliminate them. And so we arrive to this transformed integrand in its simplest form. So we have the integral of negative dz. And the integral of negative dz is equal to negative z as c. Substituting the value of z from our given information, we get the final answer, negative the quantity 1 plus x raised to the power of 4, all raised to the power of 1/4, divided by x plus c. But how did we get this value of z, by the way? Take note that expression x raised to the power of 4 times z raised to the power of 4 equals 1 plus x raised to the power of 4. We can manipulate that expression to find the value of z. Applying and manipulating algebraic operations, applying laws of exponent, we get the value of z. And so we have the final answer. Now I would like to uh, present the references that I used and the links of included images and tip arts and suggested online readings. Thank you for listening. Stay safe and healthy.